Okay, so today's announcements are just that the exam regrades are due noon on Wednesday. So if you haven't gotten yours back from either me or your recitation TA, odds are pretty good you will not be in a recitation that meets before noon on Wednesday, so you might need to email your TA and either drop by their office hours or figure out some other time to meet up with them. If nothing else, if you're having a hard time setting up a time that works to meet with your TA to get your exam back, maybe have them drop it off in my mailbox and then you can just come pick it up from me whenever. I've done that for a couple of people already, and actually one person who's doing that, I have your exam here. I don't know what you look like, but I know your name, sorry. But we can get that back to you that way. But one way or another, just make sure you get a hold of your exam before noon Wednesday if you think you might want to submit regrades. And then in case you've missed any of my announcements about how to do a regrade, pretty much just staple a piece of paper on the front of your exam saying, please regrade problem such and such. And then once the deadline passes, I'll go through the whole stack and figure out how I want to handle things. Okay. Questions about that? Okay, cool. Alrighty, so today we are continuing on with chapter 17. It's actually a very short chapter, so we might finish it up today, pretty likely, and then next time we'll get into chapter 18, which is quite a bit longer. Okay, so chapter 17, we're still looking at allylic and benzylic reactivity. Okay, so last time we looked at carbocations at the allylic or benzylic position. Turns out they're way more stable than they would be otherwise. And we also looked at radicals at the allylic or benzylic position, which are also more stable than they would be. And we saw one new reaction, which is NBS, which is just for doing radical addition to the allylic or benzylic position. One thing that I didn't mention before that I realized I need to talk about is NBS. It does do radical addition, radical halogen addition. But because it's actually a source of sort of less reactive radicals than Br2 is, just because the other half of the NBS molecule, once it splits off from bromine, I think is relatively more stable with the dot, the radical electron, than a second Br dot would be. It's actually not reactive enough to react with tertiary protons on the molecule. Tertiary hydrogens on the molecule, I should say, because there is no deprotonation step. So one thing I need to specify is NBS does radical halogenation only at the allylic and benzylic positions. So if we have some alkyl group like this, even though this would react with Br2 in light and would stick a bromine on to replace the hydrogen coming off of here, NBS on this is going to be slow enough. I'm not even going to redraw that. I'm just going to write no reaction here because it's just not reactive enough to go for non-allylic, non-benzylic places. Okay. So any questions about that one? Okay, cool. Alrighty, so we've looked at plus charges, we've looked at radicals. Kind of makes sense that the next thing that we're going to look at is negative charges. So reactions with a negative charge on carbon, or a carbanion. Okay, so just like the common theme in this chapter, is the same here. Anytime you have a negative charge at the allylic or benzylic position is going to be way better off than it would be otherwise. So the most common place that we've seen negative charges on carbon so far is organometallics, which is what we're going to be looking at here. So as a reminder, the two organometallics we've spent the most time with so far, Grignards and Organolithiums. So Grignards are carbon attached to a magnesium, and organolithiums are carbon attached to a lithium. We can draw these either in the covalent form like this, or we can draw them in the ionic form where, because carbon's the more electronegative atom out of this bond, it takes both the electrons out of there and takes a negative charge, and so the metal is left with a positive charge. Okay, so because these molecules behave as if they have a negative charge on carbon, anything we can do to make an organometallic metal attached at the allylic or benzylic position is going to be way more stable than it would be otherwise. And in other words, we know that the pKa of these molecules is usually pretty high. So like pKa about 60 something if it's just a regular alkyl group with all sp3 carbons. It's going to be way, way lower for a allylic or benzylic position. I don't think I included the actual pKa numbers, and I don't know off the top of my head what they are, but many tens of units lower would be my guess. Okay, so how this looks for allylic stuff is, say we're looking at an organolithium that's in the allylic position here. We know that we can draw this as, and whether we show this as radical or as an actual reaction step is a little bit up in the air. We are showing sigma bonds breaking and forming, so it's kind of iffy whether it's actually resonance or not. However you show it, I'm probably going to be okay with. So carbon with a negative charge there, lithium with a positive charge there. But as soon as we do this, we're looking at something where we've shown resonance forms on this molecule or something pretty similar to it before. So why don't we just boot that over to there. Put the negative charge there. And that gets us this molecule, which we can also show rejoining the lithium at this location. So I guess I should really draw square brackets around the whole thing because we can treat the entire set of 4 structures as all different resonance forms of each other. Okay, so that's kind of what we're dealing with. The lithium can be shown as bonded to 2 different places in an allylic system. Which, since this is not a symmetrical molecule, as soon as we do any reaction where the organolithium actually reacts with something, say reacting it with water so it picks up a proton, we're going to get potentially 2 different products out of that. Okay, so questions about this? Okay, so let me actually show the proton step. So basically, if we take this and react it with water, we're going to get not just this molecule where the proton sticks on exactly where we'd expect, but we're also going to get this product as well, where we do the carbanion resonance form and then the proton sticks on. Okay, so questions about that? Yeah. So I guess we haven't really talked about Carbana instability, but it turns out it's actually the opposite of carbocation stability, where carbocations want to be as substituted as possible. Carbanions want to be as unsubstituted as possible because having more R groups around contributes more electron density through hyperconjugation and makes them less happy about that. So this would actually probably be the more dominant form, but I don't know if it ends up being like a kinetic or thermodynamic dominated kind of thing. My guess would be kinetic, which means that probably this would be major. But yeah, I don't know for sure. So, Okay. So other questions about that one? Okay, cool. Alrighty, so we're going to look at a fourth category here, which is actually sort of unexpected, but it kind of makes sense based on what we've covered so far. And that is reactions that don't officially have formal charges, but that still get some charge density going at that position. So reactions without formal charges. So they can still have partial charges that develop and then dissipate as we go through the reaction. Okay, so again, we're doing a whole lot of review of Chapter 9, alkyl halide chemistry here. Turns out that the two reactions from that chapter that we haven't covered yet, which is E2 and SN2, this is where they're going to fit in. So we know that E2 and SN2 never officially make any charge on carbon. Turns out that they do briefly generate sort of a partial positive. So E2 is actually going to give delta negative charge at the carbon getting deprotonated. So the carbon that loses an H. And it never stays, it's just like during the actual transition stage, right when we're at the sort of peak energy on the energy diagram. So how that looks, and I'm going to show this for the benzylic position because that's kind of a good way to stabilize it. Okay. So we're used to showing sort of, we have a base come in, maybe let's use ethoxide, because that's what I got in the notes. It comes in, it takes the H, this kicks down, that boots out the bromine. Really, you should have anti-periplanar geometry, but I'm being pretty vague about stereochemistry on this one. And normally we would just show it going straight to the final product without sort of lingering on the transition state. But if we actually want to dig into how that looks, we can show our partial bonds being broken and formed during the transition state. All right, so I'm going to do square brackets around this and say double dagger. So officially this is not part of the mechanism that you would have to show, but we can sort of show any transition state that forms. Okay, so that's the bonds that stay intact the whole time. But we've got a partial bond to bromine because it's getting kicked out during the reaction. We've got a partial CC double bond, or pi bond forming there. We've got a partial CH bond. Okay, and then a partial OH bond here. As it turns out, so actually that's no longer minus, that's delta minus now. And the bromine is also delta minus. We know this because afterwards, when we show the products, we're going to have Br minus over here. So bromine started neutral, ends negative. At the midway point, it should have delta negative. And for O, it starts negative, ends neutral, so at the midway point, it should also have delta negative. So we know these two end atoms of the whole chain of breaking and forming bonds have partial negatives at this point in the reaction. What also turns out to be the case that we haven't really looked at before is this carbon, sort of the third in the chain of 5 atoms involved here. This is also delta negative. So this is actually part of a pattern that tends to happen a lot during reactions, which is alternating polarity. So I guess we have seen a little bit of this where Let me write this up. So alternating polarity, where we have delta minuses on every second atom. This is actually kind of a really common pattern which we've seen in a few other reactions. So for example, if we have, say, a benzylic resonance form, say we're looking at carbocations, we've shown through resonance that we can distribute the plus charge out to every other atom around the ring. So really if we want to show like where on average the plus charge is located, it's going to be sort of every other atom around the system by resonance forms. And if you go back to, I think I showed it at the page 1 of this chapter's notes, you can sort of go through and see that that's all of the atoms where the charge ends up, and they're all alternating around the whole system. This is a really common pattern. Anytime you have a charge, you can sort of distribute the charge out onto every other atom along the chain. And it turns out to be the case for transition states as well, where you have a little bit of delta negative developing at this carbon. Okay, so what this means is that even though we never get a full negative charge on here, like we go officially from neutral carbon to neutral carbon, we're actually getting a bit of delta negative developing there during the mechanism. And so having the benzylic position available to it means that we have stabilization of the charge here, and that makes the reaction go easier. Okay, so note that this is different from SN1E1 reactivity. So here, if we want to do E2 and take advantage of the benzylic position, we actually got to have the halogen one further carbon away from the benzylic position. So kind of a good tip-off that E2 might be more favored than it would be otherwise is you've got the halogen one further away from the benzylic position, which means that the benzylic position itself is going to be very easy to deprotonate during an E2 reaction. So if we do have the halogen right at the benzylic position, that's going to favor preferentially either SN1 or E1 or SN2, which we're about to cover. Okay. Okay, so questions about this? All right, cool. So that's kind of my cue to start talking about SN2. So SN2, we know officially there's also no charge on anything. But we do know that based on the transition states for SN2, the one carbon sort of at the center of the reaction is going to go sp2 hybridized briefly. So I'll draw what that looks like. Okay, so so here's a leaving group with our nucleophile coming in. very briefly, if we show the transition state here, we're going to this sort of pentavalent looking carbon where it's got 3 full bonds to the 3 uninvolved groups and then like 2 half a bonds sort of to the other stuff. Here it's sp3, here it's sp2. So if you showed the orbitals here, like both the nucleophile and the leaving group would be sort of affiliated with the 2 lobes of this p orbital that's sticking out front and back of the carbon. And meanwhile, the remaining 3 groups, the H's in this case, are all still just bonded to regular sp2 hybrid orbitals. So we're sort of changing the hybridization of carbon real briefly so that we can flip the stereochemistry. So if you remember, this is kind of like when I showed the lone pairs inverting on a nitrogen, sort of like flipping the umbrella on nitrogen inside out. Let me draw that up here too, because it's kind of cool and relevant. So nitrogen's lone pairs here, I think I've drawn this up a couple times, start out sp3, but can briefly go sp2, which means the lone pair is in a p orbital briefly, and then when it goes back to sp3, the lone pair could be on the left side or the right side of the nitrogen, which is how it does that inversion of stereochem thing. So it's actually really similar to what's happening to the carbon during SN2. It's just that carbon, instead of having a lone pair that it can just pop out one side or the other with like no repercussions at all, like nitrogen can, carbon actually has consequences for it because on one side it's got a nucleophile that it could end up bonded to, and then on the other it's got a leaving group that it could end up bonded to. Okay, so given what we've talked about with p orbitals and pi systems and aromatic rings, looking at something with a p orbital here might make you think that being next to an aromatic ring, there might be some interaction going on there. And it turns out that's the case. So if we're doing SN2 at the benzylic carbon, then we can stabilize the p orbital that forms. By overlapping it slightly with the pi system of the aromatic ring. So how that might look is, okay, so here's benzene hanging out with its pi system, like 2 separate kind of donut-shaped lobes above and below the actual carbon ring. Say we have another carbon hanging off to the side, and it's bonded onto, say, a bromine down here. So here's the CBr bond, and then there's the little nub of the hybrid orbital lobe sort of sticking out the back. We know that the actual orbital that the nucleophile is going to have to overlap with when it comes in is sort of hanging out the backside of the carbon. That's the LUMO orbital for this that we need to overlap with. So when the nucleophile comes in, we're going to do backside attack on this carbon. And briefly, so right now we're sp3 on that carbon. Briefly, we're going to go to this carbon having a p orbital. And it turns out, even though it's not officially part of the pi system of the ring, so long as it's like oriented the same, so like if it happens to be lined up so that it's vertical, the same as all the p orbitals on the ring, the way I've got it drawn, you can actually get some stabilization where, okay, that's a mess, but it looks better in the notes when I drew it in ChemDraw. But there is actually some overlap between the p orbital on this carbon here and the nearest pi orbital lobes on the benzene ring where it's attached to. So it gets stabilized by doing that because the carbon, like going sp2 when it's trying to hold on to 5 groups at once, is pretty high energy for SN2. Okay, so in practical terms, this looks like it might not be that big a deal. It turns out it's actually a huge deal for stabilizing. Having this orbital overlap actually speeds the reaction up by about 5 orders of magnitude. So about a factor of 100,000 times faster, just because it's benzylic, than it would be for the equivalent non-benzylic molecule. Okay, and if we're doing it allylic, I'm not going to draw the whole thing, but there is a similar kind of overlap where you can get some stabilization from the pi system. But it's nowhere near as powerful as it would be for benzylic, which sort of is not too surprising. We know there's a whole lot of pi system stabilization going on in benzylic systems that is above and beyond what we get just from resonance with allylic. So we would expect like there's some huge orbital magic going on if we can tie into that with the p orbital during the reaction. Okay, so questions about that? Okay, cool. All right, so the last reactions that we're going to cover in this chapter are actually more similar to stuff that we saw in the alcohols chapter with oxidations, but we're going to see again some specific stuff that's useful for allylic and benzylic. Okay, so as kind of a review here, we're used to seeing primary alcohols, so like, say this one here, propanol. We can do 2 different levels of oxidation onto that. Either we hit it with PCC, which its whole deal is it maxes out at the 2 bonds to oxygen state. So we're going to make either the aldehyde or the ketone at best out of this. And we're doing that by pulling H's off and adding new bonds to oxygen coming off of the carbon. So here we had on the carbon 1 bond to O and 2 to H. And we're going to end up with 2 bonds to O and we're left with just 1 bond to H. So that's for PCC, which is a milder oxidizer. Or if we want to hit it with the big guns, we can do, there's like half a dozen ways to write this, but in the notes I have CrO3, you can write Jones, you can write like any sort of chromium heavily oxidized salt that we've seen before, like dichromate or chromate. But all of them do the same thing, which is they're going to replace every bond to H with a new bond to O. So here we've got 2 bonds to H we could afford to lose. So we're going to end up with a total of 3 bonds to O coming off of that carbon, which looks like a carboxylic acid. So replace every H with an O at the carbon that had an O to begin with. So at the carbon with the O, with the oxygen. Whereas PCC over here is it maxes out at 2 CO bonds. Okay, so hopefully that looks pretty familiar. Any questions about that one? Okay, we can also show this for secondary just for comparison. So if we're doing secondary here, again, PCC maxes out at 2 bonds to O. That puts us there. Or Jones and similar. Are going to replace every bond to H with a new bond to O at that carbon, which actually for this case happens to give us the same thing that PCC does. So for secondary, you can't actually tell the difference afterwards between whether PCC was used or whether Jones was used. They both get you to the ketone. Okay, so that should be old news. We've seen that since chapter 10. What we're going to look at now is some oxidizers that only go after allylic or benzylic. So they're kind of like NBS. They're very picky for allylic and benzylic positions. So we're looking for something that's a little bit more selective and is only going to go for allylic or benzylic. So the first one we're going to look at is MnO2 is basically PCC for allylic and benzylic only. And it turns out that's just because it's an even weaker oxidizer than PCC, and it needs the little extra boost of benzylic and allylic being easier to react with. So we can show this one reacting with MnO2, and we'll do the same thing that PCC would. And the same for benzylic. MnO2 is going to react that just like PCC would do. But if we tried doing MnO2 on something that's not allylic or benzylic, nothing's going to happen. So like if we take the same primary alcohol from up here and MnO2, it's going to be no reaction. Okay, so questions about that one? All right, so for most of the oxidation stuff, I don't really go into the mechanism for it. If you're curious, I think the MnO2 mechanism is either in the textbook or in the study guide that goes with it. But really, for these oxidizers, I'm more focusing on the overall reaction and not getting into the mechanism of how it works. Okay, so MnO2 is pretty weak sauce for an oxidizer. The other one that we're going to look at is kind of on the opposite range of how reactive it is. Okay, so I guess for all of these oxidizers that we've seen so far, the common theme is that we're starting with at least one bond to oxygen. So we start with either an alcohol or, I guess I didn't show it as an option, but you can start with something that's already partially oxidized. So let me actually add that in here. You can start with the aldehyde here, oxidize that with Jones, and you'll get to the same point. But in all these cases, it's got to have at least one bond to oxygen on there. Turns out, you don't even need that if you're benzylic if you use the right reagent. So this works for benzylic only. Even if there's no oxygen there. So long as there is at least one hydrogen. So at least one benzylic H. This is a very unusual oxidation reaction because it kind of breaks the rules that we've seen so far for every other oxidizer, which is that all we're doing is replacing bonds to H with bonds to O. So like all of these ones up here, we pulled off an H, we added a new bond to O, we're done. This one is actually reactive enough that not only is it breaking CH bonds, it's going to break CC bonds. Okay, so as long as we start with at least one benzylic H on there, we're just going to rip off everything else that carbon has and replace it with oxygens. So let's start out with like a simpler example. Okay, so this where we have CH3, we're going to use an oxidizer that we've actually used before. Like this is kind of in the family of stronger oxidizers like Jones. It turns out that this one is actually a little bit more reactive than the rest of its family. KMNO4, potassium permanganate, turns out to be the most reactive out of all of those. But even then, this is still kind of a difficult reaction, like usually heat and long reaction times are going to be necessary to sort of cook all these groups off of the carbon. But ultimately, what you're going to get is everything else on that carbon, aside from the benzylic or the aromatic ring itself, gets pulled off and replaced with new bonds to oxygen. Okay, so here that's not too impressive looking. All we're doing is replacing H's, but here we've got a carbon with two other carbons on it. Let me draw those explicitly. All right, so carbon with an H and two methyls coming off of it, so like an isopropyl group, in other words. KMNO4, and eventually N, heat and time. Will actually get you exactly the same product. Like both of those methyls are coming off of there just because that position is susceptible enough to oxidation that the whole thing is just going to come off. And you're going to end up with a carboxylic acid on there. Okay, so questions about that one? Okay. So the one limitation on this reaction is if you don't have any benzylic H's, then nothing can happen. So if no benzylic H, then no reaction. So in other words, the only way you can avoid this happening is by just doing some sort of quaternary carbon on here, so like a T-butyl group coming off of the benzene ring. KMNO4 is going to be, nothing happens there. Okay, so questions about that one? Yeah. It's not a hindered thing. It's just that having an H or an OH on that position sort of gives this thing an opportunity to come in and rip off the H and sort of start oxidizing and like chipping away at the oxidation state. And without that, it just doesn't have any sort of like, I guess, oxidative foothold on it, kind of. So sterics might come into it too, but mainly it's just like there's nothing to rip off of this carbon to get things started. So. And again, we're not going to go through the whole mechanism for it, but it basically is sort of, once you get one of the groups pulled off and replaced with oxygen, you can actually start cleaving carbon-carbon bonds. Not directly analogous to, but sort of similar to how you might do ozonolysis, where you end up like sort of inserting oxygens into the carbon-carbon bond, but it's only got some similarities to that. Okay. So that's actually it for the reactions in this short chapter. The last thing that I'm going to do in the last 5 minutes is a synthesis practice. And then I am going to set the due date for this homework 1 week from today. Okay. So let's make this thing. Okay. So right away I'm looking at this and I'm realizing I may have a problem, because what kind of directing effects does this group have? Is it meta-directing or orthopara? Yep, and this one? Okay, some confusion. So remember, you want to look at the atom that's directly attached to the ring. This one has a double bond to a more electronegative atom, so this is also meta-directing. Both of them are meta-directing. It doesn't matter that this thing has lone pairs on an atom further out. What matters is the thing directly attached to the ring has a delta positive on it. So anything with a carbonyl at the point where it attaches to the ring, that's going to be meta-directing. Okay, so questions about that? Does that make sense? Yeah. Hmm? Hmm? Yep, so that's making this much more difficult. So they're meta-directing now, but now that we know something we can do to convert a group on the benzene ring into a carboxylic acid, maybe we can stick on something that did have the right directing effects, then get stuff on how we want it, and then trim things up so that maybe they look different at the end. So that's kind of exactly where I'm going with this. Okay, so we know that we can make this from pretty much any alkyl group that's not quaternary at the carbon where it attaches. From almost any alkyl group, like an R group. And we know that R groups are OP directing. So we're going to have to take advantage of that. So let's stick on an orthopara directing group, use that to stick the nitro on in the right place, and then turn this into something else that's how we want it to look at the end. Okay, so let's just go through that in order. Start with benzene. Let's stick on an R group, and we have a lot of freedom here because we know that the oxidation step at the end is just going to chew up pretty much any alkyl group we want to stick on there. Let's be efficient and have high atom economy and just stick on like a single carbon so we don't have to waste any atoms. AlCl3 gives us the Friedel-Crafts reaction here, CH3. Now we have an orthopara director that puts things where we like for this product. So now we can nitrate H2SO4. CH3, and then nitro, and we're going to get the ortho as well. we're just going to have to say discard that. Not much we can do about selectivity between ortho and para, unfortunately, most of the time. So assuming that we just do the separation, get the para by itself, now we can take this alkyl group that we want, hit it with KMNO4, and that'll get us to the product that we want. Okay, so I guess the take-home message is, just because you've got the wrong directing effects in both groups for what you want, you can now start tweaking what the groups actually are, and that might actually flip their directing effects in ways that you can control. Hi.